TLC can be used to identify substances. For example, if you have authentic samples of compounds that you know could be present in a mixture, for example, in this illustration, the mixture consists of compounds A, B, and C, you can identify the mixture components by spotting the mixture and the authentic samples on the same TLC plate. Identical compounds on the same plate will have the same RF values and the same visualization characteristics. So each mixture component should travel the same distance and exhibit the same visualization characteristics as the corresponding authentic sample spotted on the plate. In this illustration, after the plate is eluted, all spots within each TLC lane are visible under shortwave UV light. When the plate is placed in an iodine chamber, authentic compound A is stained a dark brown, authentic compound B is stained a light yellow, and authentic compound C isn't stained at all. Since the lowest RF spot in the mixture lane at the far right on the plate has the same RF as authentic sample A and is similarly stained by iodine, we can identify that spot in the mixture as compound A. Since the highest RF spot in the mixture has the same RF as authentic compound B and is similarly stained by iodine, that spot in the mixture must be compound B. And finally, for the same reasons, the remaining spot in the mixture lane must be compound C. In the previous example, TLC was used to identify components in a mixture by spotting on the same TLC plate the mixture along with authentic compounds thought to be present in the mixture. In that example, all components in the mixture being analyzed had very different RF values. That is, they were all well separated on the plate, making it easy to confidently match the RF values of mixture components with those of authentic samples. Moreover, the mixture components had different visualization characteristics, making identification even easier. But what if the components in a mixture had only slightly different RF values, and they also had the same visualization characteristics? Is it at all possible to identify components in the mixture by TLC comparison versus authentic samples of compounds thought to be present in the mixture? In some cases, yes, using a technique called TLC co-spotting. What follows are illustrations of why and how this technique could be used. First, let's address why anyone would need to do TLC co-spotting. In this example, we're just trying to confirm the identity of an unknown sample that consists of a single component which we believe could possibly be compound A. So in the usual way, we spot in separate lanes both the unknown and an authentic sample of compound A on the same TLC plate. Once the plate is eluted and eluent solvent evaporated and the spots visualized, we find that although the unknown and authentic A have the same visualization characteristics, their RF values appear to be slightly different. Or maybe the eluent went up the plate a bit crookedly at a slight angle, making the RF values that should be the same appear to be slightly different. How can we be confident that they are the same compound, or maybe just two different compounds with similar RF values and the same visualization characteristics? We can use the technique of TLC co-spotting. In this example, we see how TLC co-spotting can be helpful. We again spot in separate lanes on the same TLC plate both the unknown suspected to be A and an authentic sample of A. But in a third separate lane, we also spot both the unknown and the authentic sample directly on top of each other at the same location at the origin. After the plate is eluted, the eluent evaporated, and the spots visualized, we see separation of spots in the co-spotted lane. Since identical compounds will have the same RF when spotted on the same plate, that is, they will travel the same distance from the origin, if the two spots separate when co-spotted together in the same TLC lane, then they must be different compounds. However, what if we performed the same analysis by co-spotting both the unknown and authentic A at the same location at the origin, and after eluting and visualizing the plate, we see no separation of spots in the co-spotted lane? Well, if the two co-spotted spots co-elute, that is, they don't separate on the plate, then it's reasonable to assume that they are the same compound, that is, the unknown is indeed A. In any case, even if the two spots co-eluted, the identity of the unknown compound could be firmly established to be A by further analyzing it using common spectroscopic techniques that reliably determine the structures of organic molecules, such as nuclear magnetic resonance, that is NMR spectroscopy. But TLC co-spotting is a quick and straightforward way to establish the identity of a compound versus an authentic sample. What follows is a demonstration of TLC co-spotting. First, obtain a small silica gel TLC plate. The plate will most likely have one short end where the silica gel doesn't reach the edge of the plate, and another end where the silica gel coating extends to the very edge of the plate. If so, at the edge with the exposed glass, use a ruler to lightly draw a straight line 1.5 centimeters from the edge of the glass. Do this by lightly dragging the pencil across the plate's surface with very little pressure to avoid scraping any silica gel off the plate. This line will serve to mark the solvent front. In some instances, the distance from the edge should be 1 centimeter or less. Consult the experimental procedure for instructions. From the other end, use a ruler to lightly draw a pencil line 1 centimeter from the very edge of the plate. This line will serve to mark the origin along which you will spot the plate. Along the origin, very lightly make 3 small marks equidistant from each other and from the edges of the plate. The TLC plate is now ready for spotting. For this demonstration, at the 3 marks placed along the origin will be spotted the product mixture from the hydration of 1-hexene at the far right, an authentic sample of 3-hexanol purchased from a chemical supply company, spotted at the far left, and in the middle will be co-spotted both the product mixture from the hydration of 1-hexene and the authentic sample of 3-hexanol directly on top of each other at the same location at the origin. Standard solutions of authentic 1-hexanol, 2-hexanol, and 3-hexanol dissolved in volatile solvents like dichloromethane will be available for use. Here, a standard solution of authentic 3-hexanol is taken up into a clean, unused TLC spotter and then spotted at both the far left lane and at the center lane at the origin. Remember to immediately replace the cap on the standard after you're done with it. Next, a solution of the reaction product mixture in dichloromethane is taken up into a new, clean, and unused TLC spotter and then spotted at both the far right lane and at the center lane directly on top of the 3-hexanol standard that was also spotted there. Remember to recork the test tube containing the reaction product mixture and place the tube upright in a secure location. The plate is now ready to be placed in a TLC chamber. Prepare the TLC chamber by adding the appropriate volume of eluent and then wetting the filter paper wick. Use your gloved hand to carefully place the plate in the developing chamber. Position the plate in the chamber such that the top corners are resting against the filter paper wick and the silica surface is facing away from the paper. Immediately cover the chamber with its lid and leave it undisturbed until the eluting solvent reaches the line marked for the solvent front. When the eluent reaches the pencil line marking the solvent front, remove the plate from the chamber and replace the chamber lid. If needed, the eluent can be reused repeatedly, but at the end of the experiment, remember to discard it according to the instructions in the experimental procedure. Next, you must evaporate the eluent from the plate's surface. You can hold the plate with forceps while drying it for about 30 seconds with a heat gun set on cool. Do this step in a fume hood to avoid inhaling solvent vapors. You can also place the plate flat on the bench top to dry it while holding the plate down with forceps to prevent it from being pushed along by air from the heat gun. The plate is now ready to be visualized, in this case using an ethanol solution of phosphomelibdic acid, PMA, since the spots don't visualize with either UV light or iodine vapors. Hold the plate with forceps or your gloved hand and dip it quickly in and out of the PMA solution. As you would with all other chemicals, avoid direct contact with the PMA solution since it's corrosive and thus an irritant to skin and eyes. Allow the heavy drops of solution to drip back into the jar before touching the plate to a paper towel. Immediately heat the plate surface with the heat from a heat gun positioned about 2 to 3 inches from the surface. Keep heating until components on the plate appear as dark spots, and then stop heating after a further 10 seconds or so. Continued heating may make the spots fade. You can see that the visualized component spots appear a very dark green against a lighter green background. The visualized TLC plate shows 2 distinct spots in the reaction product lane, a more intense spot at lower RF and a less intense spot at slightly higher RF, suggesting the presence of one major component and one minor component in the hexene hydration reaction product mixture. You can also see that the less intense higher RF spot co-elutes with authentic 3-hexanol in the center co-spot lane, suggesting the identity of the higher RF reaction product spot to be 3-hexanol, and this should be confirmed by a more definitive analytical technique such as NMR spectroscopy. For a more complete product analysis by TLC, the reaction product mixture should be co-spotted separately versus authentic samples of 1-hexanol and 2-hexanol.